All right, we're going to continue to 3.3. So that's we're gonna look at relative standings and box plots. So before we get into this, the box plots are gonna have to do with, if you guys remember. So here, hit stat, go to calc 1 var. Today we're gonna finally look at these values here. Let me go down. These Q sub 1s. If you can't see, let me zoom in. That Q sub 1, Q sub 3. These are what we're going to use today to make those box plots. So we're going to finally see how those work. Let me get out of this. But before we get into that, let me move that. Let me just talk about what this relative standing is. So 3.1 was trying to find the measure of center. So that was the mean, median, mode. So that was looking for the most common data value, depending if it was, you had to think about if it was qualitative or quantitative. And then we looked at measure of variation. So that was the range, standard deviation, variance. And that just showed us how spread apart our data values are. Like if we were to put our data values on a number line. So for the variance and all those, that definitely dealt with qualitative variables. With qualitative, we didn't measure the variation because there's no way to, if you're talking about names, how far apart names are from each other, there's no order to them or numerical value measurement. Where quantitative variables, since we could measure them numerically, if we put them on a number line, we can see how spread apart our data values are. But if we don't have our data values, depending what our standard deviation is, remember, the bigger the range was. So that was, let me just go back to it since I have it up right here. So remember when we looked at the range, it was the largest value minus the smallest value. And that just gave us an idea of how big the window of our values are. And the bigger the range was, that just meant how spread apart the more spread apart your data values are. The smaller the range was, the closer your data values were together. But the problem is the range wasn't resistant, because there could be one very small number and then it might seem like your range is very large when technically majority of your data values might be really, really close to each other. Like if you're trying to look at the variation of ages within your group of friends. Imagine you had friends that were 18, 17, 20, 19, 21, 23, and roughly all you are within your late teens and early 20s. But then you happen to have one friend that their dad likes to hang out with you guys, and their dad is like 60. If you just looked at the youngest was 18 and the oldest is 60, let's say if that dad was part of the friend group, it would look like you have friends that are in their 30s. Because if you just look at the range, it would give you a window from 18 to 60, and your window would look wide. You would think that you have friends that are in their 30s and 40s and 50s, but it just happens to be one person that's 60. So that sort of skews all your information. If you don't take that 160 out, your range would be a lot smaller because your data values are a lot closer. So that's why we use the standard deviation, because the standard deviation helped us, took every data value into account. So even though it was a very large number, it wouldn't be affected as much as the range would be. So the standard deviation based everything off the mean. So that was looking at the center, or the most common data value, and then going from there trying to determine how spread apart your values are. But it worked the same way. The larger the standard deviation was, the more spread apart your data values are. The smaller your standard deviation, the closer your data values are. Where even if you got a standard deviation of 0, we did an example of that, and that was right here when we did. So you hit stat. So remember, it's a stat class. I hit 1 to go to my table, and we did the example of just all 7s. You can see that that's just for column 5, all 7s. And if I tried calculating my standard deviation, so the mean, the median, standard deviation, all those were in the same place. And that was under stat. Move 1 to the right to 1 vars. You either hit 1 or enter. And then just make sure you put the correct list. So that list is L sub 1. Ours was an L sub 5. So that's right here. So I'm going to hit second and then 5. And that gives me L sub 5. So then I'm going to go to calculate. I hit enter. And then there's my standard deviation of 0. Because all the data values are exactly the same. So there is no deviation. They're all in the exact... Like if you were to put all those on a number line, you only have 1 dot at 7. So there would be nothing spread apart. So that was just some things that we looked at. But now we're going to talk about a relative standing. So the measure of standing was just looking for the most common one. The variation was measure variation was trying to see how spread apart all of them are. A measure of relative standing is just looking at one. So let me get out of here. So that means I just want to know where one data value is compared to the rest. Like when we did a relative frequency, we took one row of frequencies and we compared it to the rest of them. So if you think about like in a competition and you look at standings, that's like who's in first and who's in second, who's in third, but your focus on and second means you're behind first, third means you're behind first and second. So that idea of relative standing is where does this one data value lie or compare to all the other one? Like where are they on the number line? So there's a way to try to see where one data value is. And this is a very important idea that we're going to be seeing a lot in when we look at later chapters. And that's a z-score. So the z-score is the number of standard deviations that the given value x is above or below the mean. So that's why I wanted to talk about the standard deviation. Remember, the standard deviation told you how spread apart your data values are. But the z-score can tell you exactly where one of them is. The standard deviation, if we went back, we just knew that, remember the empirical, if you're within one standard deviation, that was one above and below, 68% of your data values should be within one standard deviation of the mean. But that's just telling you, again, we don't know how many data values you have. We just know 68% of them should be within one standard deviation. I'm not worried about all of them. What the z-score is helping me do is show me what's happening to one of them. That's why here, this x here represents that one data value that you're worried about. Just one of them, not all of them. But you're telling me where this one is relative to the mean. It uses the standard deviation. It's like saying that you are 3 feet away from me or 3.5 feet away from me. We can think about the feet as our standard deviation. That's our form of measuring things. And every standard deviation changes depending on your data set. But you're using the standard deviation sort of as a length to see how far it is away from the mean, and is using standard deviations. It's like when you say, I'm 3 feet away from you versus 3 inches away from you. We understand that a foot, again, this is on a camera, but hopefully a foot is roughly, let's say this far apart, where an inch would be this far apart from each other. So we have that understanding of what that measurement is, that length. If we're talking about 3 inches or a mile, we understand these are different lengths. And you could be 1 mile away, 1 foot away, 1 inch away. but we already have knowledge of how much that distance is. When you get a z-score, the z-score is just telling you how many standard deviations you are. And depending, like I said before, when you're calculating your standard deviation, it uses the same units of measurement. That's what makes it really nice. So if you're talking about feet, your standard deviation, let's say if you're talking about like a long jump, and you got a bunch of long jumpers, and they all jump within 8 feet long, 10 feet long, 11, 12 feet long, and you calculated a standard deviation. The standard deviation is going to have the same units of measurement. It's going to be in feet. It might be half a foot, 3/4 of a foot, 0.23 feet, but it's still based off a foot. So depending what the units are, the z-score is going to tell you how many standard deviations you are away from the mean. And every data set is different. Every data set, if I turn this on, I go to stat, and then remember, so let me back out. I hit stat to go to my table, and on edit, I either hit 1 or enter, and it'll take me to the same place. Like, these are all different data values. All of these. Let me just remove this one here. I'm deleting it. Not clearing, just delete that one data value. And then I can try to see a standard deviation here. So calc 1 var. But that was second. That's L sub 1 here. I want to change it to. So when I calculate, that's my standard deviation here. So a 16.45, whatever this could mean. I think that example was talking about BPMs, something like that. But depending on the data set, it's always different. I can now try to calculate the standard deviation of my second data set. And now this has a standard deviation of 1,860. So again, it's always going to vary depending on your data set. But that's already 1,806 of whatever that means. Same way of, we just know because of experience that this is a foot and this is an inch. But every standard deviation is going to be different. So you just want to know where one data value is, and that's what this X represents. One data value. And then this is using sample notation, this is using population notation. So this is a sample mean, that's a sample standard deviation. This is the population mean, and this is the population standard deviation. So that's why it was really important at the beginning of the semester. We spent a lot of time talking about sample and population. Population was the entire group, a sample is a subgroup. So if you calculated the mean from the subgroup, that mean is a sample. If you calculated the mean from the entire population, so let's say if you're trying to, like, I always use the example of finding the average height of PCC student. If you asked all 30,000 students and you calculated the mean, let's say you put all their heights in one of these columns. Let's say you put all 5,000 again, which that'd be ridiculous to put 5,000 here. There's other programs to use, but let's say you inputted 5,000 here, and then you calculate, or you inputted all 30,000, and you calculated the mean. That would be a population mean because you asked everybody. But let's say you only asked 5,000. And you put those 5,000 in this column, and then you calculated the mean, that would be a sample mean. So the context of the question will determine if it's a population or a sample. Same thing with the standard deviation. So remember, we're getting the standard deviation, all those are in the same place. So there's our sample mean, and there's our sample standard deviation. Again, the only time that you know that this isn't the sample is if you know that the data set is implying that it's the whole entire group, that it means the population. Then you would use the population. You would say this is the population mean, and this has the population standard deviation. So you can see sample, population. These both mean standard deviation. This is just the sample, the S, and this is the lowercase sigma. And that's your population standard deviation. So the description will tell you if it's a sample or if it's a population. Like when we did the example about marijuana for medical use, they said they only asked 1,500 U.S. adults. It doesn't say it's a sample anywhere in the description. Did it say it was a sample? But we knew it was a sample because there's more than 1,500 U.S. adults. The fact that they only asked 1,500, that implies it's a subgroup of there's millions of U.S. adults. So sometimes you have to take on your knowledge to be able to determine this. And you would have whatever data value that is. So let's say if you're talking about the average height of PCC students, if you just wanted to see where one particular, like if your height, where it stands relative to everybody else, you would take your height subtracted by the mean. So whatever you calculated your mean, if it was a sample or population, and then you divide it by the standard deviation. And then you're going to get a number, and that number is going to tell you how many standard deviations you are from the mean. Remember, we said the standard deviation is always positive because it's just telling us how spread apart our data values are. But the z-score can be negative because if our data value is smaller than this number, if you remember from arithmetic, we always keep the sign of the bigger number. So if the mean is bigger, that means this overall number is going to be negative because I know the standard deviation is always positive. So, but if my value is bigger, then I know this is going to be positive. So if your z-score ends up being negative, that just means that your data value is to the left of the mean. If your z-score is positive, that just means your data value is above the mean or to the right of the mean. And when you're doing these calculations, it's really important to remember that when you're doing your z-scores, you want to make sure you're rounding them to 2 decimal places. So if there was one more number here to the right, you have to determine if that number is going to tell you to make this go up or it's going to stay the same. But you're always going to round to 2 decimal places. And after we do some examples, you'll see that. So just remember, z-scores always round to 2 decimal places. Always, always, always. So that's what this is saying here. A z-score is the number of standard deviations that a given value x is above or below the mean. So if it's above, it's going to be positive. If it's below, it's going to be negative. And it's basing it off the standard deviation. And the standard deviation is going to have the same units of measurement as your data sets do. So maybe your data set is in seconds, in feet, in weight, length. It's going to have the same units of measurement. So it'll give you a rough idea of where the data value is. It might be 2 standard deviations from the mean, and then the standard deviation might be like 3 feet or 0.3 feet. So it's going to be 3 of those below or above, depending if you're positive or negative. And then a data value is significantly low if its z-score is less than or equal to -2. And then a data value is significantly high if the z-score is greater than or equal to +2. So what that means, we have to think about, if we remember this empirical rule, we know that so this is 1 standard deviation. Again, if it doesn't strictly say above or below, then you just assume it to be both. So 1 standard deviation from the mean, all this represents 68%. 2 standard deviations represents 95%. So that's where the z-score of this would be 2 and -2 If it's anything here or above, that's why it says it's either significantly high or significantly low. Because remember, these data values here, you can think about this as your number line. And there's your mean right at the center. And then your data values fall. If you actually put them on the number line, they'll be spread out across this number line. But 68% of them will be somewhere within here. So there'll be a bunch of numbers next to it. And then there'll be more spread apart. But 2 standard deviations, majority of them should be within here. So if you actually had your mean here and you actually tried plotting all your data values, if you had them, there will be majority would be in here. And that's why it's saying that anything above positive 2 standard deviations, so that's anything above this, would be significantly high. Because the majority of them should be in here. If your data value is somewhere in here, that means it's extremely high. Or if it's over here, that means it's extremely low, because there should be very few. Look, even here it says 0.13% of your data value should be here. So that's very, very small, meaning very few data values should be above this 2 or below these standard deviations. But these would be, that's why it's saying, whoops, wrong thing. That's what it says, significantly low if the z-score is less than -2. So that's saying it's negative if it's 2 standard deviations below, or even more than that, or it's 2 standard deviations above, or even more above than that. And that's, majority of values shouldn't be there. So if a data value is in those left and right tails, that's significantly low or significantly high if it's on the right or left. All right, let's look at an example. So this here, comparing a baby's weight and adult body temperatures. Again, does baby weight and a body temperature have anything in common? We're not asking if they have anything in common. Right here, we're just saying which of the following 2 data values is more extreme relative. So remember, relative is, you're talking about, like, relative is, for you, is like your brother, your sister, someone who is in your family who's related to you. So each data set, each question was talking about baby weights. So you're looking at that data compared to baby's weight. You're not going to try to compare it to body temperature. That's what it means by relative to the data set from which it came. So the first one says 4,000 gram weight of a newborn baby among 400 weights. So don't get that mixed up. You're saying there's a baby that weighs 4,000 grams, and that means you don't, among 400 weights with the sample mean. So it's telling us this has a sample mean of 3,156 grams. That means they're looking at 400 different babies and their weight. So remember when we were talking about identifying the sample, the population, the statistic, the parameter, the variable? So again, the variable in this situation isn't just the baby, it's the weight of a baby. And here they looked at 400 different weights. And one of them is 4,000 grams. Now, we're going to find the z-score of this data value. So I want to know where this data value is. So again, we want to see like which, and then here, there's 99 degrees Fahrenheit temperature of an adult among 106 adults with a sample mean of 98.20 and sample standard deviation of 0. So this is what I mean by the standard deviation uses the same units of measurement here too. The sample standard deviation is 693.4 grams. So all these babies, 400, again, I don't know what all these weights are. I know one of them is 4,000, and I know the mean of the 400 is 3,152. And the standard deviation is 69.4 grams. So that gives you an idea of a weight, of an amount of how spread apart these are from each other. So that means if you were to add 693.4 to the mean and subtract this to the mean, that would give you, that means there would be roughly about 68% of those 400 should be in here. Yeah, we don't know what those data values are. If we had, we can actually list them out and then we can count to see if 68% of them are there. But as long as it's normally distributed, or sorry, it's like a bell shape and symmetric, then it should follow these rules. So let's go back to the question. All right, the second one was, they looked at 106 adults. One of the adults had a body temperature of 99 degrees Fahrenheit. But then you got the temperature of 106 of them, and then you calculated the mean. So let's say if you wanted to actually find, if you actually had the data set, we would go to stat. Again, go to our table, and then we input all those body temperatures, and then we'd calculate the mean. Same thing for the baby weight. We would put on all 400 weights in grams. So don't forget that this isn't just any random weight. It's talking about the weights of the babies in grams. And then you would calculate your mean based off all that data. But since we don't have it, it's giving us our mean. So that's, which of the following two data values is more extreme relative to the data set from which it came from? So this is coming from this data set, and this one's coming from this data set. And we're just trying to see which one of these is more extreme. So that means if we're looking at these, the data values, do they land? Is one of them too far left, too far right, and we're going to compare them to each other. Again, not saying that the body temperature and the baby's weight have a comparison. Maybe they might, maybe they don't, but we're not trying to see if there's a comparison. We're just going to look at the z-score. So we want to know the relative standing, meaning I want to know where this data value lies, and I can do that. The z-score can tell me that. So that means we're going to calculate the z-score of these two. So if we look back to the formula, and remember everything was sample. So the description telling us it was sample. So we're going to use this formula here that it's the data value. So for the babies, it was 4,000. That's the data value. We're going to subtract it by the mean, which was like 3,100 and something. And then the standard deviation was like 600 and something. So let's actually do those calculations. So that's what we see here. So the solution, 4,000 gram weight and 99.6 Fahrenheit. Those are we're finding the z-score for those two. So again, that's the data value, sample mean, sample standard deviation. Oops, wrong way. So here we have 4,000 grams minus 3,152 grams divided by 693.4 grams. So that's the sample mean, sample standard deviation. And we get a z-score 1.22. So what that means, it's saying that this data value is positive 1.22 standard deviations. And since it's positive, that's how you know it's going to be above the mean. It's 1.22 standard deviations above the mean. You can think about it. And what's the standard deviation? It's this. So it's 1.22 of these away from the mean. And if you wanted to find what that is, it's like taking this number and multiplying it to here. Because it's 1.22 of 693.2. So it would look something, again, you don't need to do this, but it would look something like this. So remember, second quit to get out of that table. So we do 6 93.4. Hopefully you guys can see these numbers here. Times 1.22. So that's how many grams away it is from the mean. Again, that's not saying that it's exactly where it is. That's just, we know the mean is 3,152, and that's how many grams it is away from the mean, above the mean. Which makes sense, because that's how, if we just look at this distance away from each other, that's how many grams, roughly how many grams those are away from each other. Now, if we look at the body temperature, so we have the variable we're looking at, so we're just looking at one data value, is 99 degrees Fahrenheit, minus the sample mean. So we go back, here's our sample mean, sample standard deviation, minus 398.2 degrees Fahrenheit, divided by 0.62. Oh, wait, there's a slight error. Oh, you guys see that? This is 92.20. I don't know where the 300 came from. That's weird. So, can't take it off, but just fix that. Should be 98, and which, if you actually tried calculating this on your own, you wouldn't get this number if you use 392.8. It has to be 98.20. So if we look here, because our sample mean is 98.20 degrees Fahrenheit, that wouldn't make sense. Because remember, the mean is the most common data value, and if you were 398 degrees Fahrenheit, you'd be dead. You'd be melted. That's so hot. So our body temperature is not 398.20. That's not a mean. That's not an average body temperature. So take out that 3, and let me do it right here on the side. Just when you're doing like fractions like this, remember, if you remember from algebra, when you're doing order of operations, you want to make sure you take care of the numerator first and then divide. And you can do that by using these parentheses here. So these parentheses, I'm going to put 99 minus, not this 390, I'm going to put 98.2. You don't have to put the 0, but since it's there. So this is telling me I'm going to subtract these first. Then I want to divide. Then I can put my division symbol and put point. If you want to put the 0, you put 0.62. Or you could have just subtract this first and then do the division. But if you wanted to plug it all in at once, you have to use these parentheses, because that's saying, because if you were to not put the parentheses, it's going to divide this number and then subtract it here, which you can't do that. You would have to subtract first and then divide. So the parentheses tell the calculator to subtract first and then divide. And then when we'd enter, again, there's that. Let me get a little closer. You see 1.29, which matches this 1.29. If you were to put 398, you would get something completely different. So, again, if you don't like putting it all in one, you could just do 99 minus 98.2. So again, don't put that 3, it's a typo there. You can do this subtraction first, as long as you know that needs to happen first. Do that subtraction. And then if you want, you can put 0.8 here, or if you just push divide next, because I want to divide it by 0.62. Oh, okay. That's not what I meant to push. So 99 minus 98.2. You can hit divide. Now that I did this already, I want to divide that. And then it gives you this, whoops. It gives you this A and S. What that means is looking at the answer. And what it's doing is using the answer from the previous operation. The previous operation was subtraction. So that means I'm going to take the answer and I'm going to divide it by 0.62. And there we still get 1.22. So nothing there is changing. So if I go up, see, we still, from when I did it all in one line. The nice thing, this sort of keeps track of everything that you do. So it's all in there. If you scroll up, you can always find everything you calculated. Or, and you could have easily have just put 0.8 divided by 0.62. And every single time you're getting the same answer. So you just want to be careful when you're plugging into your calculator. I know it seems silly, but a lot of errors happen when we're trying to put everything all at once because these calculators don't use order of operations. So you want to be careful when you're doing that. All right, but now we're looking at these z-scores, and they're both positive. So that means they're both to the right of the mean. So to the right of this 98 and to the right of this 3,152. Because they're positive, they're to the right. And we didn't get numbers like bigger or smaller than -2 or +2. But if I'm comparing these, which one do you think is more extreme than the other? And remember, the idea of being extreme is being further to the right, because the further you are to the right, because remember, the majority of them should be in here. That's why that area looks bigger. The majority should be in here. Extreme values are in the tails on either above or below. And even though these values are not bigger than +2 or smaller than -2, I'm just comparing to see which one of these is more extreme. So since we know that this standard deviation is big, this z-score is bigger than that one, that means it's further to the right. The further to the right, that means the more extreme that you're getting. If you're further to the left on the negative side, that means the more extreme you're getting to the left. But since this one's bigger, we'd say that this value is more extreme, because the question was, which one of the following two data values is more extreme? I'm not saying that they are really extreme, just which one of them is more extreme. So yeah, the z-scores show that 4,000 gram birth weight is 1.2 standard deviations above the mean, and the 99 degrees Fahrenheit body temperature is 1.92 standard deviations above the mean. Again, because that's what the z-score is. It's how many standard deviations away from the mean, either above or below. Because the body temperature is farther above the mean, it is more extreme value. So 99 degrees body temperature is slightly more extreme than the birth weight. Again, it's only slightly, because 0.29 is just a little more than 0.22. That doesn't mean they are really extreme, because they're not above 2 or below -2 z-score. But one is more extreme than the other, just because one is farther away from the mean. And that's how you can sort of compare some of these z-scores. And again, it depends on the context of when you're comparing them, which one is more extreme than the other. For example, let's say we're looking at the Angels. So this is looking at baseball, the Los Angeles Angels, and the Colorado Rockies. Again, if you know nothing about baseball, you can think about just sports in general. And normally in sports, whoever scores the most wins, or is considered the better team because they can score more points than the other one. So in this situation, we're saying that determine whether Los Angeles Angels or the Colorado Rockies had a relatively better running producing season. So by runs, we can think about them as scores. So who scored more points throughout the entire season? So not just one single game, is if you add up all the points that they made in each game all together, saying like how many points did they get in all of them. And those of you who know baseball, hopefully, again, I don't personally know much about baseball, so hopefully I'm not wrong in that scenario, but the idea is who scored more points. But something that you do need to know about baseball is, well, let's look at here. It says the Angels scored 733 runs and play in the American League, where the mean number of runs scored was 67.4. And the standard deviation was 51.7 runs. The Rockies scored 755 runs and play in the National League, where the mean number of runs scored was 640 and the standard deviation was 59.9 runs. So if you're just looking slowly at these values, you can see that the Angels did more runs than the Rockies. But the thing is, one plays for the American League and the other one plays for the National League. So again, I don't want to get too much into how baseball works, but the idea is just imagine that they're playing for two different leagues. That means they play each other in the season. I'm not too sure about baseball, but the idea is if we're looking at two different leagues, we're trying to see how did they do compared to the teams in that league versus the teams in the American League versus the teams in the National League. So in the American League, the sample mean, or the mean, is 677.4. So that's looking at all the teams. So that's, now you're thinking more of a population because it's not taking a few of the teams. It just says where the mean number of runs. So the American League, where the mean number of runs scored was 677.4. So you're assuming there that they checked every single team, and every single team had calculated getting all the runs, including the Angels. All of them came out to a mean of 677.4. So that's more of a population. They didn't ask a few of the teams. They checked all the teams in the American League. And then in the National League, they checked all their teams and their mean was 640.